right, we have a graph of f of x equals x cubed. And I put this b here to show that we're going to try to evaluate by a Riemann sum the interval, the area under this curve from 0 to b, where b is greater than 0. And we're going to divide this interval from 0 to b into n subintervals. And then eventually we're going to let n approach infinity and see what happens. What's the limit of this area under the curve as n approaches infinity? First of all, we're going to have a regular division of this interval. The length of the interval is b minus 0. And we're going to divide that into n subintervals. So the width of each subinterval is b over n. That's this little distance right here, b over n. To find an expression for the right-hand endpoints, think of it this way. The first right-hand endpoint will start at 0 and add on one of these b over n's. To get to the second right-hand endpoint, we'll start at 0 and add on 2 of these b over n's. And to get, in general, the ith right-hand endpoint, we'll start at 0 and add on I of these b over n's. So there is an expression for the right-hand endpoint. So to find the area of a typical rectangle, that's this one right here, we're going to put the right-hand endpoint into the function, which is, where does it say that? Oh, right here. X cubed, there it is right there, times the width of the rectangle. So there's a formula for the area of the ith rectangle. And we're going to have n of them. Here's another one right here. Obviously, as we move to the right, each area will get a little bit bigger because the function value will be a little bit bigger. And now we want to sum these rectangular areas from I equals 1 to n. We're going to have n rectangles. So we're going to take this expression right here and see if we can get it just in terms of n's. B is a constant, by the way. So is n. I could say n from I equals 1 to 100. So n is just a constant. So I can move b to the fourth over n to the fourth outside the summation symbol. And I've got the sum from I equals 1 to n of I cubed, and that's where this formula comes in right here. I can replace this summation with n squared times the quantity n plus 1 squared over 4. If I square this n plus 1, distribute the n squared, and then divide by this n to the fourth, moving this 4 to the left, b to the fourth over n. This is what I get. And now I want to take the limit of this expression as n approaches infinity. And what I've done is reduced n to the fourth over n to the fourth to a 1. 2n cubed over n to the fourth is 2 over n, and n squared over n to the fourth is 1 over n squared. As we take the limit of this expression as n approaches infinity, these fractions approach 0. So the limit is b to the fourth over 4. And of course, if we evaluated this as a definite integral, we would raise the exponent by 1, multiply by the reciprocal of the new exponent, evaluate from 0 to b, and we'd have 1/4 b to the fourth minus 1/4 0 to the fourth, or guess what? 1/4 b to the fourth. So that's how you evaluate the definite integral using a Riemann sum. There you go. Hope that helped. And if you have any questions, post a comment.